Hey, okay. So this video I'm gonna talk about the SSE, which is the uh, sum of square error. Now the formula for the sum of square error is like this. So n equals 5, for example. It's not always gonna be 5. So don't just say 5 always. If you don't know what I'm even doing here, search up summation notation. Khan Academy's summation notation. This just means sum, right? So I'm assuming you already know all this. The formula is, let's see. Oh, I have no idea why I put an equal sign. So essentially, this is the formula to calculate your sum of square error. Essentially what this means is this value, this is our observed value. That just means the actual y points, and I'll explain this in a second. And this is our predicted value, or estimated, you can say. So what does that mean? How do we even get y hat? Y hat is calculated like this: bo plus b1x. So, and actually I forgot, this should be squared. Sorry about that. Essentially what this is doing is, for each data point, it's subtracting every single y value minus our prediction. So say we do y hat, or say y 1 is equal to bo plus b1 times 1. So we are estimating the first value. This is y equals mx plus b. You should know what I'm doing. So we're pretty much estimating the first value in our data set. So say this x, y. I'm just gonna make random data. Doesn't really represent anything. And 1.5 maybe. So when we do this, we're estimating the first value, right? Obviously, because we're doing bo plus b1 times 1. So essentially, and actually let me wait, no. So essentially what this means, for example, in this case, y, so our actual observed value, so that will be 1.5 minus our predicted value. So say this gives out, I don't know, say this gives 1.7, for example. It's probably not going to be, we don't even have an equation right now or anything. Just pretend this is an equation and it gives 1.7. We would do this, and this will equal our SSE for the first value. And then we would essentially square that, and then we would add it 5 more times with the rest of the 5 points in our data set. So the next one is gonna be y2 is equal to bo plus b1 times 2, and say that outputs 3.1 or something. Now what is this doing? This is estimating our second value, right? So all we do here is, and actually I'm gonna erase this right here because that should not be there. So say, let me find my okay. So our observed value, so 3.1 minus, or sorry, the observed value is 3.2. So 3.2 minus our predicted value, so in this case 3.1. So boom. So we do this for each data set, right? We subtract the observed value by our estimated value with our equation. And this equation, we're going to obviously find with linear regression. That's the entire purpose of it. So now I'm going to erase all of this. And just give me a second because it's pretty slow. So now you know what the sum of squared error is. I'm just going to give you some more ideas. The entire purpose of it is to test the effectiveness, I guess, of our linear regression algorithm. So yeah, so right now we're not going to use this because when we have a data set, and I'm going to graph this up. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This is our y, this is our x, and I'm just going to plot these. So 1 and 1.5, and they should go here. 2 and 3.2. Oh, sorry, 2 and 3.2. 3 and 2.9. And 4 and 3.8. 4 and 3.8. And 1.5. And you know what? I'm gonna make this 2 to 2.1. No reason, just to make this look nicer. So 2.1 and 2.2. So right away, we can tell there's a linear regression between this. I mean, not a linear regression, sorry, a positive linear relationship. And obviously, we want to find the line of best fit to be able to make better predictions and estimations. Now, the problem here is we don't have a line of best fit. So what do we do if we don't have a line of best fit? I'm going to do this in this color. When we don't have a line of best fit, the best thing we can do is do n equals 5, I equals 1. The best thing we can do is we can subtract our observed values. So y minus the mean, right? This is, again, just the best we can do in this moment. So y minus the mean. Actually, let me do that. So this is literally the same thing, except we don't have any equation, so we can't actually do this up here because we don't have an equation for our line of best fit right now, right? So the best we can do, and actually I'm just going to keep this crossed out, the best thing we can do right now is to just find the mean and subtract each observed value by the mean. So how do we find the mean? That's pretty straightforward. You just add up all the values and divide by how many there are. So 1.5, 3.2, 2.9. And if I do anything wrong, just pretend like it's right. It's really late. So you just add up all the values and you divide by how many there are. So 2.72. So our mean, and this little line on top, that's the mean sign. And I completely forgot what it was. 1.5, 3.2, 2.9, yeah, okay. 2.72. So 2.72 72. So our best estimation for the average value right now, the average outcome you can say, is the mean. So 2.72, right? You can see it's pretty good, but obviously this is going to be horrible for predictions later on. Because say we have a data point around here or here, our predictions are going to be pretty terrible. So now it's literally the exact same idea, except we're just subtracting by the mean. And this, so yeah. So our observed values, 1.5, 3.2, 2.9, 3.8, and 2.2. We're going ahead and subtract each of these by the mean. Mm, 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 mm. So what's our mean? 2.72. So 2.72, 2.72, and so on, right? Now, the question is, what do we call this? What do we call this a result right here? So the result of each of these is called the residual or error. I like to call it the error. You can call it the residual, and I'll write residual up here. So residual slash error. So each of these individually, they're gonna be called the error, right? So you get that now. And the sum of squared error, right? So you just take these values and you square them. So that's what it means by sum of square error. You just square each of these and you add them all up, right? The sum. So how far these points are from the mean, that's going to be called a residual. So that is, so the distance between the, so the distance between the y and the y and the mean, the observed value and the mean, that's going to be a residual. Call it whatever you want, error, residual, whatever. So we take all these values, so 1.5, and so 1.5 minus 2.72. So negative 1.22. So negative 1.22. And then 3.2. So 3.2. 0.48. So this is 0.48. I'm sorry. It's 2 actually. So this is going to be 0.48. 3 and 2.9. So 2.9. That's going to be 0.18. Right? So that means it's going up by 0.18. And then 4 is 3.8. So 3.8. So this is going to be 1.08, right? And then finally 2.1 and 2.2. So 2.2 minus this is going to be negative 0.52. So now we take all these numbers and we square them. And obviously when you square a number it becomes a positive. So don't be worried about that. So I'm gonna go back on each number. I'm gonna square them, and then I'm gonna just add them all up together. Pretty straightforward. Wait, yeah, okay. So just take every number, square it, and then just add them all up, right? So the sum of those square values. Pretty straightforward. And I'm not rounding these up just yet because it's a little too early. And you're going to be working with bigger numbers. Right now we're seeing these with very small numbers. You're going to work with way bigger numbers. Right, so just add all of these up. So again, you're going to be working with bigger numbers. Your sum of square error is usually going to be very high, like 100 to like 1000 originally is going to be like that high. So right now it's obviously 3.88, which is really not that high. So right now our SSE is just say 3.2. So our SSE is going to change, and I find that the best way to keep track is with the SST. If you don't know what the SST is, it's the sum of square total. So instead of E, just total. So our original is going to be 3.2. Now the reason I say this is because our SSE is going to change later as we actually find the line of best fit. And actually it's going to be around here. As we actually find the line of best fit, our SST is going to change. So it's not always going to be 3.2, but our SST is a good way to keep track of that value. So this is how we find the original SSE, right? And let me just remove this so it doesn't get confusing. So this is how we find our original SSE when we don't have a linear regression and we want to get an idea of what it is. So we get the mean of our y values, we plot it, we get the residual or error of each point, which is the observed value minus the mean, and then we square every single one of those and add them all up together, and we get our SSE. And later on, we want to, so I'm going to put this in red, we want to reduce SSE, right? And in the next video, I'm gonna actually use this equation.